Welcome back. So, you probably tried adding vectors by just, sketching them out. It's great for getting a picture in your head, but let's be real, it can be a little, imprecise. Well, today, we're ditching the rulers and protractors. We're going to dive deep and master a much more powerful and way more precise way to do it, the analytical method, using vector components.
So here's what we've got on tap. First, we'll talk about why we even need to go analytical. Then we'll deconstruct vectors into their components and grab the trig tools we need. After that, I'll show you a super straightforward 4-step method, we'll walk through an example together, and finally, we'll clear up some common tricky spots that trip people up.
Okay, let's get right into it. Why are we doing this? I mean, we can draw vectors to add them, so why go through the trouble of a whole new mathematical approach? Well, it all comes down to precision, something that's absolutely critical in physics. Look, drawing vectors head to tail is awesome for visualizing what's going on. It really is. But, and let's be honest here, how accurate is it really? It's pretty much limited by how steady your hand is and how good your protractor is. And in physics, we usually need way more precision than that. And this is exactly where the analytical method comes in and just blows the graphical method out of the water. Instead of sketching, we use math, specifically trigonometry. And what that gets us are results that are super precise and totally repeatable. The only limit is the accuracy of the numbers you start with, not how well you can draw a straight line.
All right, now for the really cool part. The absolute magic of this whole technique is that it lets us take a tricky two-dimensional problem and split it into two simple one-dimensional problems. It's like a divide-and-conquer strategy for physics. And the secret ingredient that lets us do this is a huge concept, the independence of motion.
So how do we do it? We take any vector and we resolve it, that's the fancy word, into its perpendicular components. A really good way to think about this is to imagine they're the shadows the vector would cast on the x-axis and the y-axis. You'll get an x component and a y component, and if you add those two little vectors back together, you get your original vector. It's that simple. Now, if you remember one thing from this whole explainer, make it this. Motions along perpendicular directions are independent of each other. Seriously. What a vector is doing horizontally has absolutely no impact on what it's doing vertically, and the other way around. This idea is the foundation for, well, pretty much all of 2D physics, from throwing a baseball to sending a rocket into orbit.
But here's a really important catch you've got to watch out for. The component vectors, yeah, they add up to the original, but their magnitudes, the numbers themselves, don't just add up. Think about it. If you walk 3 meters east and then 4 meters north, you didn't travel 7 meters from your starting point, right? No, you're 5 meters away. That's a classic 3-4-5 right triangle, and it's a perfect reminder of how this works.
All right, so this is all great in theory, but how do we actually find the numbers for these components? Well, it's time to open up our trigonometry toolkit. And don't worry, you'll see it's really just a couple of simple formulas you probably already know.
So let's say you know the vector's length, its magnitude a, and its angle theta. Finding the components is just some basic trig. Remember SOHCAHTOA? The x component is the adjacent side of the triangle. So that's going to be a times the cosine of theta, and the y component is the opposite side, so that's a times the sine of theta. Easy as that.
And guess what? It works backwards too. If someone gives you the components, you can put the original vector back together again. The magnitude? That's just the hypotenuse, so we use our old friend, the Pythagorean theorem. And the angle? For that, we use the inverse tangent of the y component over the x component. Opposite over adjacent.
Okay, we have all the pieces. We know what components are, and we know the trig to find them. Now, let's put it all together into a simple 4-step recipe that you can use to add any number of vectors. And I mean it. This process is foolproof.
Here's the 4-step plan. Step 1, resolve. You take every single vector you're adding and break it down into its x and y parts. Step 2, add. This is the easy part. Just add up all the x components to get a total x, and add up all the y components to get a total y. Now you have the components of your final answer, which we call the resultant. So, step 3 and 4 are just calculate. You use those new total components to find the final magnitude using Pythagoras, and the final direction using inverse tangent. That's it!
All right, enough talking about it. Let's actually do it. We're going to put this method to the test with a real example. I'll walk you through it step by step so you can see exactly how this whole process works in practice.
Okay, here's the problem. Imagine someone takes a walk in two parts. First, they go 53 meters at an angle of 20 degrees north of east. That's our vector A. Then, they go 34 meters at 63 degrees north of east. That's vector B. The question is, what's their final displacement from where they started? We're looking for the resultant vector, r.
All right, time to execute our four-step plan. Step 1, resolve. We'll set up a little table to keep things organized. For vector A, the x component is 53 times cosine of 20 degrees, which gives us 49.8 meters. The y component is 53 times sine of 20, which is 18.1. Now we do the exact same thing for vector B. Its x component is 34 times cos of 63, and its y is 34 times sine of 63. Okay, step 2, add them up. We just add down the columns. The x's sum to 65.2, and the y's sum to 48.4. And those are the components of our final answer.
We're almost there. Step 3. Calculate the magnitude. We take our resultant components, our x and our y, and we pop them into the Pythagorean theorem. So the final magnitude, r, is the square root of 65.2 squared plus 48.4 squared. Punch that into your calculator, and you get a final displacement of 81.2 meters.
And for the grand finale, step 4, calculate the direction. We just need the inverse tangent of the y component divided by the x component. So that's the inverse tangent of 48.4 divided by 65.2, and that gives us our angle, 36.6 degrees. So let's put it all together. The final answer is a resultant vector of 81.2 meters at an angle of 36.6 degrees north of east. And we're done.
Okay, before we call it a day, I want to quickly go over a couple of common questions that often trip students up. Getting these straight will really lock in your understanding of how all this component stuff works.
So here's a good one to chew on. Is it ever possible for one of a vector's components to have a magnitude that's actually bigger than the vector itself? What do you think? Just based on the geometry, the right triangles we've been drawing, is that possible?
And the answer is a hard no. It's impossible. And the reason is simple geometry. The vector itself is always the hypotenuse of the right triangle, and its components are the other two sides, the legs. And as we all know from math class, the hypotenuse is always the longest side. The only way a component can even be equal to the vector's magnitude is if the vector is pointing perfectly along one of the axes, which just means the other component is 0.
And one last thing to think about as we wrap up. We've talked all about adding vectors, but what about subtracting them? How would you handle a minus b? Well, think about it. Subtracting b is exactly the same thing as adding a negative b. And a negative b is just a vector that points in the opposite direction. So what do? You just flip the signs of its components. That's it. So you see, with this analytical method, subtraction is just as easy as addition. It's an incredibly powerful tool to have. Thanks for joining me.